Okay, so let's review a little bit of the exponential functions. So you saw that an exponential function looks of the form y equals c times a to the x. Just like a linear function is y equals mx plus b, an exponential function looks like this. And if a, which was called the factor, is greater than 1, we have a growth, and this is how the graph looks like. The function is increasing. And if it's between 0 and 1, we have a decay. And then the graph will look something like that, decreasing. Okay? So then, for example, we could have f of x equals 200 1.2 to the x. Since a is 1.2 and is greater than 1, we basically have a growth. Okay? So a is 1.2. We have a growth. And we say that with the growth rate of 20%. How did I get the 20%? Basically, it's what is after the after the point, and you have 0.2 right after the 1, so that means 20%. So in a decimal is 0.2, in a percentage is 20%. If you have, for example, f of x equals 500 times 7.75 to the x, since this a is 0.75, which is less than 1, we have a decay. And the decay rate is basically 1 minus 0.75, which gives you a 25.25, which is in percentage is 25% decay. Okay? So in general, if you have a growth rate, a growth factor, a, the rate is going to be, so the rate is going to be your factor a minus 1. That's how we got the 20%. The factor was 1.2 minus 1. We got that it's 0.2, which gave us the 20%. And if you have a decay, how do you get the decay rate? The decay rate is 1 minus the decay factor. Okay, so this is a formula that you need to remember. How to get the rate if you're given the factor. You also saw there are some other types of exponential forms. So for example, actually let's go and do an example. Let's see if I can move this. So if you have an initial population of 633 and the population grows by 15 people per year, this doesn't say by 15%. It just says that every year the population increases by 15 people. So you start with 633 and then you add with each year t or x, you add 15 people. So this is just a linear equation. So when with each year it grows by a constant amount, that's linear. If the population doubles every year, basically that means that I start with, it says with 1831, and it doubles. So the first year will be times 2, right? And then the second year, the population will be whatever it was the first year. So 1831 times 2, double that, right? So basically with each year, the initial population is multiplied by a factor. So that is the case of exponential functions. So this is the same as saying 1831 times 2 to the 2, because 2 times 2 is 2 squared. So in general, after t year, you will have that the population is 1831 times 2 to the t. Okay? So if the population changes by a constant amount every year, then we have linear. If the population changes by a constant percentage or is multiplied by a factor, then then is an exponential form. Notice that multiplied by 2 means an 100% increase, right? Doubles means it increases by 100% of what it was. Okay, so if you remember, if I wanted to get the rate is what we just said earlier. The rate is the growth factor minus 1. So the rate for this case will be 2 minus 1, which gives you 1. And this is like an integer, right? And percentage 1 means 100%. Okay, so let's look at another type. So notice that now it says that the initial population is 316 and that the population doubles every 13 years. So every time you hear this every 13 years, this is your cue that you need to use another form of the exponential function. So basically you're going to use the f of x equals c times, I think we call it b to the t over k, where k is that every kth period. That's what k means. So since for this one we have that the population, so our function is not f, it's called p, and we start with 316 and it doubles every 13 years. That means that k is 13. So t will have t over 13, and b, the growth factor, will be 2 because it doubles. Okay? So then every time you hear that the growth or the decay happens every 13 years, every 5 hours, every 10,000 years, so every time you hear that, basically you're going to use this formula where k represents every kth period. Notice that for these problems, the yearly growth factor is basically just b to the 1 over k. So the yearly growth factor means that t is 1. Yearly means that t is 1. So basically, instead of looking at the growth factor as b to the t over k, you look at b to the 1 over k because t is 1 in a year. All right. What about this one? The initial amount of substance is 547 grams, and the amount of substance decreases by 80% every 15 years. So again, you see every 15 years, so immediately you're like, okay, I need to use this formula, c times b to the t over k, where k is 15. So let's rewrite it, and I start with the initial amount of 547, and then k is 15. So I'm going to put t, and I just need to decide what is b. It says that it decreases by 80%. So how do I show that in the decay factor? I don't put 80% in here, because if I put 80% in here, that means a 20% decrease. So I need to put b is 0.2. Okay, 0.2 means, so 0.2 means a 80% decrease. If you put 0.8 in there, 0.8 would mean a 20% decrease. Okay, so this is the equation that we need. So it's basically this first one, A. So your Q is that every 15 years this change happens. So you need to use the formula with the k in it. Now another type of exponential function form is when you're dealing with a continuous rate. So every time you see the word continuous, you're going to use the formula f of x equals c times e to the rt. Okay, so every time you see a continuous, you're going to use this form, e to the rt, or times e to the rt. It doesn't matter what we call it. If we're dealing with money, we would like to call the initial p from principal. But in general, this is the formula. Every time you hear continuous rate, you write down this formula and then fill in what's given. So let's fill in what's given. In our case, the function is called p of t. See, the initial amount was, it says that initially in 1992 there were 95,820. And then I copied the y, and then the rate. I need to put in the rate as a decimal. So I looked at the rate is 1.2%. So transforming that into a decimal, I get 0.012. So this is what goes in here, 0.012t. Okay? So this is the final formula that we're going to work with. So every time you hear continuous, this is the formula you're going to use. Now, this is the case for continuous growth. When you have continuous decay, you still use the same formula. So for continuous decay, you're still going to use c times e, but the rate is going to be negative now. So you're going to put minus rt. Okay, so for this problem, it says that the substance starts with 498 grams and then it decays continuously by 15.5%. So I need to, it says, let's call this one amount. So I start with 498, e to the negative. What is the rate? 15.5% in decimal place means I move the decimal twice, so it'll be 0.155. So it'll be to the minus 0.155t. So this is the formula that I need to work with. Okay, so basically we have how many types? I would say just these types. So you'll have your regular one, which is y or f of x equals c times a to the x. And then you have the f of x equals c times b to the t over k. And then we have the f of x equals c times e to the rt for continuous growth. And then f of x equals c times e to the negative rt for continuous decay. And this one, the k1, is when the change happens every kth period of time. We also had some of the financial ones. So another formula that you need to remember is this one. I might give it to you during the exam, during the midterm. So another one was A equals the principal times 1 plus the rate over n to the nt. And this was the compounded compounded interest formula. So basically you use this one every time you hear that the interest is compounded monthly. For example, monthly would mean that n is 12, or semi-annually would mean that n is 2. So n is the number of periods, compounded periods in a year. Okay, so I hope this helps you guys decide what formula to use for an individual problem, a specific problem.